Hey, good morning, everyone. My name is Hyun Park from University of Minnesota, and I'm very excited to giving this tutorial because we have a great effort, make a lot of effort to build this large-scale markerless motion capture system, and then now finally we are able to present this to the audience in the computer vision. So we have some contributor, a lot of contributor. Without them, this cannot be made it, and so I would like to give you the brief overview of these tutorials. So the last decade, we are witnessing a revolution of the machine vision algorithm that can read the way we interact. For instance, in this video, the small boy is interacting with the young lady. And the state-of-the-art computer vision algorithm can identify the body landmark location, for instance, elbow, shoulder, arms, and in the face, eyes, nose, mouth, and also even small, tiny fingers we can detect from this single view video. Okay? It's quite impressive. But it still makes a lot of mistakes, for instance, because of the occlusion and the ambiguity in the visual semantics. So the multi-view camera system is an immediate remedy for correcting these errors. For instance, in Panoptic Studio, they use hundreds of cameras to recognize the body landmark location in three-dimensional space stably and reliably. So what are the visual cues provided by adding more views? So disparity is the first cue. Okay? So take a look at this stereoscopic image. Okay? If I draw the line on the nose of the cat, then this vertical line ends up with different location here, okay? Because of different depths. Okay? This is a disparity, and this disparity induces a 3D sensation, which allows us to triangulate the point in three-dimensional space. Okay? Disparity is the first cue. Second cue is by introducing a new camera, you can see the space behind the occluding objects. For instance, this is a single view reconstruction from the one depth cameras. And as you can see that there's a lot of hole. And this hole can be filled by integrating multiple cameras. So having a multiple camera system is beneficial. It's quite useful to correcting these errors from the single view cameras. But unfortunately, there's no ready-made multi-camera system, such as car, TV, and Vicon systems. And there are few places in the world that owns a multi-camera system. And researcher outside of this circle has a very limited access to this facility. Okay? And so now if you are outside of this circle, then you have to think about how to build a system for you. So, but this is really challenging. Because this is my system, composed of hardware frame. There's like 70 cameras. The small computer is connected to the server through this network switch, and there's a lot of wires and cables. And this is a really, really complex system, and not single component system. An entire system works only when all parts, hundreds of parts of the system works properly. Okay? So I call this as a multi-camera system engineering. That includes the hardware design to organize a camera to efficiently and effectively capture the target motion, and the network architecture that can bridge between the multimodal sensors, and the precise camera synchronization, and large-scale camera calibration, and distributed computing and data management plane, and the model representation to reconstruct the point in three-dimensional space. And then we can expand this to the real-time system, markerless motion capture system. And as I said before, entire system works only when all components work together properly, which allow us to reconstruct the unprecedented trajectory stream in three-dimensional space using by exploring hundreds of cameras. So Fortunately, we are situated in the place where we have a full access of the multi-camera system. For instance, the CMU, MPI, DRZ, and including myself. And by building this multi-camera system, we learn a lot of lessons. So in this tutorial, we would like to share our experiences, our engineering manual for building a customized multi-camera system. The goal of the tutorial is not only deploying our system, but also help you to design your customized solution. Second, the building a computational representation specific to your application. And leveraging existing data set that can be useful for your application too. So there are a lot of factors that affects your performance, your system performance. And we identify the 3 design factors that play a key role building a multi-camera system. First, precision and accuracy is the most important factor. Small, tiny error from some part can propagate over the entire system, so it can deteriorate all the system performance. And we are aimed to retain the sub-pixel accuracy in space and nanosecond accuracy in time. And your system needs to be flexible enough to integrate the multimodal sensors, such as VGA cameras, Kinet cameras, and HD camera together, okay, which has a different characteristics. Third, we are talking about the large-scale cameras, which produce big data. For instance, in Panoptic Studio, it produces 6.4 gigapixels per second. Imagine, this is like a huge number. So without any data management plan or computational plan, it is almost impossible to fully leverage the multi-view systems. So the precision, diversity, and scalability are the key design factors that will recurring throughout our tutorial. So we are very excited to have invited speakers from the 3 different institutions. Professor Takeo from Carnegie Mellon will talk about how this multi-camera system is started. Professor Theobald will talk about his real-time markerless motion capture system. And Dr. Biller and Bradley will talk about their tremendous effort to recover the subtlety in their face, okay, such as eyes, hairs, and skins. So in our tutorial, in the first session, we'll go over to the hardware engineering, how to design the space and how to synchronize the cameras and how to link these cameras together. In the second session, we'll move on to the software engineering, multimodal camera synchronization, and large-scale camera calibration, and so on, and data management, and so on. In the third session, we'll dive into the computational model, how to use multiple cameras to reconstruct the unprecedented density of the trajectory and body, face, hands. And also, we will introduce a new paradigm, new deep learning paradigm that can exploit the multi-view camera system. In fourth section, we'll go over we'll try to address a very interesting practical question. For instance, how much does it cost? How long does it take? And how many people? Shohei.
Hi, hello everyone. So thank you for coming to this tutorial. So in this session, I'm gonna introduce what was the hardware design and the structure and networking for our Panoptic Studio. So in fact, Takeo had already introduced what the CMU had in the past. And after this, so I was in Kyoto, and we built this kind of system, so with a gray background, and this was to capture the this was to capture the dancing ladies, so without having a color distribution, is the correct color, and also I was building this transportable. We are saying that this is transportable. So because I can demonstration in a day. So and in fact, we did a demonstration at the ICC 2009. So because I was a part of the organizer, and we are capturing this sort of this was a cosplayers. And in fact, so the design of the multiview camera system. In fact, so and in fact after and they say, why don't you move to Carnegie Mellon University from Kyoto? Carnegie University, in fact. So then, thinking about what is the design for the consider many components on designing that because you have a scenario, right? So I want to capture to be this large, or you need based on the object motion, you need a. And then just by considering all these dependencies, this camera, this power of the lighting, and this, based on this understanding, so the dome was a light field, complete light field. Is this a pointer? Yes. So we have a, and also we have speakers here. Microphone arrays here, and then we also have projectors. So the idea is, so if we can capture all the light events inside this room, then if we have still yet another copy of this room, right? And then, so we can reproduce the light field in a distant place, and we can have a, if this is a real-time system, we can have a communication between them. So this is a one of the, not happened, in fact, very early idea. So Takeo told me, in fact. So anyways, our philosophy was complete light field capture. The question is, to capture as many as possible light field, what we can do with a constant number of the pixels. So we have basically two options. The first one is as many as possible cameras, but their resolution is relatively low. On the other hand, so we maximize the resolution, but we have a few number of cameras. So which is better in terms of light field capture, right? So if we have a single target, so I'm not quite sure, but maybe you prefer to this strategy because we can make a better 3D details or better texture details, right? But what we see is that if we have many people inside, so as we introduce later, so our dataset has many people in the dome, so then we see that the visibility or occlusion will be the most difficult point to be solved, in fact. So then we decided, so this strategy is better for our scenario. So then, so this is the video at 2010. So to capture the light field, so as uniformly as possible, so we put as many as cameras basically on the sphere, and then so in the room, so we have several people, and each of the even though each of the cameras captures a very small portion of the scene, but because of the number of the huge number of cameras, so they can, even though they have low resolution and simple task, but because of the visibility, better visibility, we can do much better thing than the sparse high resolution cameras. So this is our design philosophy, in fact. So then, this is the final design of the dome, physical design of the dome. So this is a self-supporting structure and modular. So in fact, we were saying that we can replace the panels according to the scenario, but it is too difficult, in fact, in practice. And also, it provides a background. And for each of the panels, so we call this subgroup as a flower. So we distribute the cameras so uniform as possible. And then, so here, the most difficult part comes, in fact. So ideally, we first started from the blue dot, right? So we have something we want to do, and we should came up with the cameras. But in reality, first, we had cameras somehow, right? So we did somehow backward propagation, right? So then, so this is the final structure of the dome. So we have VGA cameras, and in the dome, so all these small dots, they are the cameras, in fact, and the large circle, they are the HD cameras, in fact. And also we have Kinects. And the background is painted in gray because it doesn't have a colored reflection. So we have a VGA camera here, so like this. And the one panel of the VGA cameras are connected to a unit. It is a PCI Express interface. And then they are controlled by a master clock generator. And also we have HD cameras and the projectors, and also Kinects. And in total, we have 480 VGA cameras and 31 HD cameras and 10 Kinects. So that means the entire system is this is a heterogeneous distributed system, right? So we have basically three groups of the cameras. So VGA camera group and HD camera group and 10 Kinect group. So in fact, so ideally, so it was better if we could design so these three subgroups somehow monolithic single system. But because we have limitations or some difficulties on choosing the cameras, so we decided that so they are three separated but loosely connected by a network system, in fact. So let me introduce, so what is the difficult point on the synchronization of these three subgroups? So in fact, we need a synchronization. Obviously, we are in computer vision, so we are interested in the 3D. So basically, so if we want to capture this object at frame t from here, so and if the next camera captures at different time instance, of course, we cannot do 3D triangulation except as non-rigid structural flow motion. So obviously, we should capture these 2 points at the same time instances, of course. So then, for synchronization, so we have basically VGA and HD cameras. And for VGA cameras, so this is from a machine vision community. So they expect the trigger signals for synchronization. Triggers means that we provide this kind of a square wave. And of course, in practice, we should have a negative logic. And then, so such triggers should be provided by what we call a pulse generator or function generator. And also for HD cameras, so this is from a production community, and they should be provided two inputs, video and audio. The video, so this is a rough sketch of what we see in the analog level of HDSDI cable. So this is the time and voltage. So these are analog signals. So for each frame, so they have somehow encoded video signals, and in between them, so we have a special signal that provides the timing information. That means the video itself provides the timing information. So as Takeo introduced in his analog video system, and we call this we call this a Genlock system, in fact. And for the reason why the camera requires audio is that the audio side provides a timestamp. So it's called a linear time code. This is regular audio signal. You can hear, in fact. But anyway, so it tells that I'm in frame 1, I'm in frame 2, or something by audio, in fact. So this kind of signals should be provided by sync generators. So that means, so for these two subsystems, we should prepare two different signals just for synchronization. And of course, so some of the cameras can be a master, and the others can be slaves. But anyway, so we should distribute this kind of system over the studio. And in fact, so in recent systems, we have a better solution. So imagine that you have three cameras right? And they say if you simply turn them on, so the images will come so asynchronously. And because these PCs are not time synchronized originally, not accurately, so you cannot know so which images are corresponding to each other, right? So you naturally say that you may introduce an NTP time synchronization, right? And then the PCs clocks are well synchronized, but basically, so this is not good enough in terms of the synchronization of the video frames, right? Because the image should go through the network and the host adapter, memory, CPU, and then after all these processings of your non-real-time OS, so you can now check what is the time in your program, right? So you cannot expect so how much of delay you see here, right? Frame by frame. So then, so this, yes. So we basically expect a global shutter, but in fact, so our HD camera is a rolling shutter system. In fact, so sorry. So then this is why. So if we anyway introduce the trigger shutters so to the camera side, so without so considering such delay, so anyway we know that so each of the images are well synchronized anyways. So that's all makes the problem easier. And we can make this point much easier, even easier. So if we introduce another network here, and the cameras can understand the PTP signal, so then all the camera clocks are also synchronized. So they are in all the same clock, world clock, and then all the capture timings can be synchronized so automatically. So this is a simpler solution, in fact, but in fact, as you may so immediately point out that the network hub here, so this can be a bottleneck. So you should provide a very nice network hub here. So now we have three options: the triggers, genlocks, and PTP synchronization. And in fact, in our system, the VGA side is triggered, and the HD side is genlocked. And for the Kinect, so we have a different solution because, as you know, the Kinect camera is not supposed to be used synchronously in the original form. So this part will be covered by Tomas later. And the difference between the synchronization shutter and asynchronous with timestamp is that if we say synchronous shutter, all the cameras start exposure at the same time instance, right? If we say async with timestamp, is that the cameras start capturing in a random timing, but we know that so for the exact timing in the global timestamp, that so this happened at frame 0 and this happened at frame 1 or something. And the difference between the triggers, we see small difference between triggers and phase lock, in fact. So if we say trigger, so if the trigger signal is in here, then the camera starts exposure a bit later. So this is called a logic trigger. And the difference is called the propagation delay. And another camera may have different delay, in fact. The difference is that so the cameras run at their own clock. And that means the camera starts exposure right after their next clock, right? So this is a difficult point, in fact. And this delay should be somehow 10 microseconds. And yes, this is totally depends on your application. So if this is OK, super fine, right? But if you are capturing very fast object, so for example, if you swing for baseball or something, so this may be an issue. So on the other hand, if you say genlock system, or in general, it's a phase lock system, all the camera clocks are synchronized, right? So that means each pixel starts exposure across the cameras exactly at the same time instance. And in fact, so for production cameras, we can use genlock, and gigabit distance cameras, we can use PTP, and for all the cameras in point gray, we could use this sync unit. But so if you see these comparisons, you may think, okay, so this would be better. But the one difference is that if you choose this synchronization, so you cannot change the frame rate depending in the capture. if we use triggers, you can issue the trigger randomly, right? So you can change the frame rate during a single capture easily. But so if we use this, so we cannot change the frame rate in practice. And also for the time code, so in the machine vision cameras, so these are not that standardized. We have no standard here, but the typical solution is that we simply embed the timestamp or any other meta informations in the first few bytes. So this is a very common technique in machine vision cameras. And also, on the other hand, for the production cameras, so as I mentioned, so the time code is embedded in basically in the audio. So that means that you should decode somehow the audio signal, in fact. And also, as Takeo mentioned, so the LTC code or audio code, this is not for synchronization. So this is just to tell you that, so which, roughly, so because this is up to 30 hertz, so roughly, so what time the frame is given. And in fact, so our system are designed to run at up to 100 hertz. So I don't know this is a standard strategy or not, but we just fast forwarded this audio signal, right? So because this is audio signal, so if we can have a 4 times faster, so then this can be upgraded to 100 hertz timestamp. So by comparing these strategies, so we see that so if we accept the additional cables for audio or LTC, so the trigger synchronization is most scalable and accurate, in fact. Or so if the PTP can be less scalable because of the limitation in the bandwidth, but the accuracy is also very nice. So in this context, so our capture system is a heterogeneous distributed system, and here is a VZ camera, and in fact the most interesting point or very original design in this camera system is here, and in fact, so this is a VZ system, and interestingly, this is a one single camera in some sense with 480 sensors. That means that we have a master clock generator, and in fact, this clock is provided to all the sensors. This drives all the sensors, and each sensor, so of 24 sensors, a group of 24 sensors, they have a output by a PCI Express, and then we have a capture node here, capture PC. So here is another group, and so forth. But in fact, so even though it looks like a camera unit controlled by a master clock, but in fact, this is designed as a single camera, in fact. So in the message in the synchronization, I would like to say that shutter level synchronization is best. And if you are designing, say, for example, multiple camera systems with 16 or small number of cameras, so maybe PTP would be better or a simple solution, in fact. And for the capture system, so we use capture system PCs for storage, computation, and also visualization or broadcasting. And in terms of the general computer science, we can consider 3 architectures, so distributed or centralized or somehow in between, so heterogeneous system. And in fact, the distributed system has the best scalability or diversity, but so the centralized system provides a easier implementation of, in our case, multi-view processing, because naturally all the camera images will be gathered into the single PC. It makes a bit easier to implement the real-time processing of the multi-view algorithms. So in that context, ours, obviously, this is a distributed systems connected through the network. So this is a heterogeneous, decentralized or distributed system. So in here, so we designed that because our system has many cameras. So we should have a distributed system for modular design, modularity. But so if we can into somehow a centralized architecture, so it was easier to implement a real-time processing, in fact. So this point was not somehow intentionally not included in the system design for our dome. So what I would do if I have, again, the huge budget by Takeo and Yaser, so at this moment, so I would propose something like this. What we are not having considered in the design of the dome is that real-time processing. So if we have a real-time processing option here, we can do visualization or interaction or feedback to the capture target for augmented reality or interaction, or we can do a real-time live broadcasting. So to do that, so now we have a hardware-based shared memory. So it's an optical interconnect. So we have a distributed camera node and distributed GPU node and also visualization node or storage node. And all of them can be connected with a hardware-based shared memory. So it simplifies the data transfer. So very simple, in fact. And in fact, so they are all available in the market. So this is a host adapter for USB, and this is an interconnect, and this is a trigger generator. So yes, in fact, I'm not saying so this is a cheap solution. So this is a expensive solution, but we can do the best, in fact. So then the discussion is that, so what is the scenario we want to use multi-view camera systems, in fact, as Takeo mentioned. So what we cannot do at this moment is that so large-scale outdoor capture or underwater capture or micro-scale capture, in fact. In the case of the outdoor, so of course, so as Takeo said, we should expect so how long cable we need. And in fact, so what is a good way of controlling the punches, robot, or lens control? In fact, this is very, very difficult. And also, in the case of the underwater, in fact, the cable itself is not so nice, right? And for the microscale object, in fact, so how to design the depth of field itself, or how to realize a multiple view is the most challenging part. And in fact, my student is presenting a poster in this CVPR for this solution, in fact. And for the underwater, so this is for fun, maybe 4 years or 5 years before. So one goldfish is captured by multiple view cameras, and this is a real-time visualization of the visual hull of this fish. So we are, as you see, that the calibration is not so trivial, right? So we should expect the refraction by the ball. But so if you can provide a good calibration strategy, so we still be able to reconstruct the 3D shape. So depending on your scenario, so we should design the cameras and the calibration and also the real-time system. Okay, so this is again the wrap-up of our Panoptic Studio, and this is a heterogeneous distributed system, and with many considerations, and also based on the limitations. Okay, thank you very much.
Right, thank you for coming our tutorial. My name is Hanbyul from CMU. And in this session, we're gonna cover a bit more software side of this Panoptic Studio. So based on the Shohei's talk, I believe you have some idea about how to choose cameras, how to place this camera, and so on and so forth. And in this session, we're gonna cover some capture software, like given this distributed system, how can we initiate this capture software to capture the sequences, and also how to save the data, and how to calibrate the data. And at the end of the talk, Tomas will be talking about how to have this multiple connected system. In our case, we have 10 Kinect, and how to synchronize and calibrate this 10 Kinect is also not that straightforward, and we're gonna share those kind of knowledge. For those who just come to this talk, this is our Panoptic Studio, which has more than 500 sensors. This is the interior of our system. You can see the small dot, that is one VJ camera. We have high resolution camera and also Kinect. And this is the captured sequences from entire of our system. You can see VJ view, high resolution view, and Kinect view. This is essentially really, really big data. 1 minute is about 500 gigabyte. And you can see how we compute this number, for example. So one VJ panel has 24 cameras that produce about 184 megabyte per second. And we have 20 panels. So VJ has 6040, 480 VJ resolution, and 1 byte is about 1 pixel. We have 24 cameras, 25 frame rate. So just single panel with 24 cameras produce that much data. In a similar manner, high resolution camera, single high resolution camera can produce this much data, and we have 31 cameras. So essentially, this is really big data, more or less compared to all other existing camera system. But although you consider a bit smaller system, you still need to handle this type of this much data, because I would like to note that the hard drive writing speed is more or less 80 or 100 megabyte, which is still smaller than single HD camera. So how to capture this type of data and how to even save the data may not be that straightforward. And this type of topics is not actually covered by any kind of papers. Although that is essentially very important when you try to build your own system. So let me just go through the capture software first. And let's just assume very simple structure. Like we have one machine, and let's say we have 3 or 4 multi-cameras connected to a single machine. And how can we make a capture software? Obviously, the industry and the company maybe provide some software. So we have maybe multi-thread software so that we can capture the camera sequence for from each thread. But what if we wanted to have like more cameras? Then because of mainly the limitation of the port or maybe storage issue, you may need to have more local servers like this. So we need to solve this scalability issue. And more importantly, if you wanted to have more diverse sensors like Kinect or high resolution sensors, the capture software may not be the same, right? You may have some different software, and you also need to initiate this software somehow at the same moment. So we need to solve this diversity issue as well. So let me just briefly, so in this topic, I'm going to just share 2 options we have applied to our system. And this is our high resolution camera system. And essentially, one single node, this is connected to 2 cameras. And let's just consider how can we make a simple capture software. We may have double thread, and we just initiate the capture software. So maybe, I mean, the problem is they may not be starting at exactly the same moment. Maybe one thread started the first capture first. So we have 1 frame here, and maybe in the next time, maybe both cameras can be captured and they saved, and so on and so forth. But fortunately, in our system, all the frames are already time-stamped by the synchronization, the hardware clock. So when we just look at each frame, they already have this timestamp so that we can have some alignment after all the captures. So this is essentially a very simple way. And based on, I mean, thanks to this timestamp, although the thread of each individual machine may not be starting at the same moment, still we can do some alignment afterward based on this timestamp. This is possible only because we have this synchronization already. And that allow us to make a bit simpler capture software system. This is actually the view we are capturing from this high resolution camera system. So each terminal is just connected to each local node. And we just use cluster SSH to connect to entire node, and we just start roughly at the same moment, the capture. So very simple capture software. But one big issue here is we cannot see the data during the capture. It doesn't provide any pre-visualization. And sometimes this is important. For example, you wanted to capture, let's say, 1 hour of the data. And during the data, maybe some issue will be happening. And you maybe want to check what's going on during the capture. That is essentially the motivation of our another capture software, which is applied for the VJ system. So in this option, in this capture software frame networking. To do that, we first initiate a local node. And local server sends to the server so that we can see all the pre-visual machine. And for the capture, the master time and the final time, so that all the captures started at a synchronized clock, and also they end at the same moment. The scene, we are actually capturing the visual system. Here you can see the local node status. Obviously, the data size is really big, so we cannot visualize entire images, but we can at least select single node and single camera to visualize that. Advantage compared to the previous simpler option is we can see the pre-visualization, and based on this networking, we can communicate, and they can start at the exactly same moment. So I have shared two options for this capture software. You may have many other options according to your applications, but two messages I would like to convey here is, if your frames are already timestamped, then capture can be very easy. You can just initiate very roughly, and anyway, you can do alignment afterward. Of course, if you need any additional convenience, you can maybe implement this networking kind of thing, which would be more complicated, but still useful in some cases. That's about capture software, and now let's just consider how to save this data, because the amount of data is not small. Obviously, we wanted to have high resolution, high frame rate, or more views to be simpler for the algorithm. But that basically means we need large size, and it's hard to say because we need this faster writing speed. For example, in our Panoptic Studio, all the cameras generate more or less 9 gigabytes per second. So you can imagine that any single storage cannot save this much data, right? Our solution, all right, before saying our solution, there can be some options. So first, you just completely ignore raw data and just save maybe processed data. That can be some small number of landmark and so on and so forth, so that you don't have to consider any storage system. Basically, that requires a real-time system because you need to process the data in real time. Maybe the second option is, okay, the data size is too big, just we can compress the data and just save the compressed data, which is essentially Hyun chose in this demo here. But in our case, although it's pretty costly, we just wanted to have this raw data. And this is our kind of goal. And our solution is based on the distributed system. So each set of cameras are already connected to single machine. And our solution is simply just put some small storage system at each node, so that we can solve this scalability issue. Another interesting part I would like to share is the amount of data from each sensor is a bit different. So we can somehow consider different strategy for each sensor groups. For example, here, VGA produced 184 megabyte, HD produced 120 megabyte, Kinect sensors produced 145 megabyte with some data annotations like depth and IR. And these are our solution. So for single node, for example, VGA, we use 3 hard drives with RAID 0 to increase the writing speed. And for others, we are using SSD. Why do we use SSD for VGA, for example? That's essentially based on our application. In our case, we wanted to capture at least 2 hours because we wanted to do some social capture where people are doing some interesting game, and that lasts about 2 hours. So one SSD may not be enough to capture those kind of things. So although this solution is not reliable, remember that RAID 0 has 100% failure rate within three years, for example. So it will be failed within 3 years. That's about the statistic. But still, we wanted to use this because of this kind of application-specific reason. Because all the storage are located in the local machine, but still we can visualize that in the operating machine by just mount the remote disk in the server. This is essentially what we are doing after the capture. So we load all the files, and we just visualize them. And one very important thing is you should copy all the data from the capture disk to the long-term storage. Otherwise, like usually you do very frequent capture in your storage, and that basically means you may have some issue in reliability. We are using NAS, and we have, I think, 15 NAS at this moment. One NAS is about 88 terabyte capacity that can capture about 2 hours of data. if you compute the number in terms of money, 1 minute is about $30, which is pretty costly. Currently, we have 1 petabyte of data so far. So some take-home message I would like to convey here is you need to consider the data size and maybe the writing speed so that you don't have any frame drop issue. Actually, for the last 5 years, we are very bothered by these frame drops because that happens very frequently. And also, you need to consider the required capacity, and you need to decouple this capture storage and the long-term storage. All right, so assuming that we learned something about how to build the system and how to capture the system, now let's just consider maybe more fun part, how to use this system, this data. And maybe the first thing you need to do is calibration. So calibration basically means we want to get these camera parameters for each camera. And there can be many other options. Maybe checkerboard is one of the common options. There exists maybe a common software like Cartech Toolbox. And one is very common for macro-based motion capture system. You may use some 3D pattern, or in the wild situation, maybe structure from motion actually provides something similar output, camera parameters. So let's just consider a simple example, just checkerboard-based method. You have a checkerboard, you just wave checkerboard, and you can get these images, and just put all the images to the toolbox, and you can get camera parameters, which is pretty simple. But assuming that, just assume that whether we can use this kind of technology to our system. This is kind of a way we do, let's just consider that if we wanted to use this kind of calibration pattern to our system, that basically means we need to wave this pattern a lot to cover entire working volume. And especially in some point, some camera cannot see the part, so we need to actually rotate a lot so that all the camera can see that. Although the checkerboard provides really good accuracy in terms of detection, we need to consider the scalability again and diversity because we need to basically cover entire working volume. And more important thing is this. In our case, we have several subsystems, and they're not perfectly synchronized because basically they don't have the same frame rate. That means sometimes at some point, maybe some camera can capture that, but some camera may not be capturing the same scene. So you need to be stationary. You need to be stop, capture, and still you need to cover entire area. And our solution is essentially something like this. This is our very initial solution. Okay, just put some tent or whatever, and just run structure from motion, assuming this is just in the wild camera system. It worked somehow, but there are issues. For example, here you cannot have any patterns on the wall side, for example. So you still move this kind of object multiple times to have some coverage. So our current solution is this. So now we are using tent, which is portable. And we just project patterns on the tent so that we have these features on the center structure and on the surface as well. So this is kind of view from different sensors. So you can see some random patterns, and you can do just safety matching. You can just run structure from motion to get the parameters. So the way is pretty kind of standard. So we just do capture first and do matching, run structure from motion. We have two phases. The initial structure from motion is done based on this single lens distortion because that is simpler for optimization. Once we have this initial kind of parameter, then we do final bundle adjustment with full lens distortions, 5 lens distortions. In reality, we capture the tent like 3 or 4 times so that we have some coverage on the center, and we merge the matching result, and we run the same structure from motion method. This is kind of the output of our calibration. You can see tent on the center. So because we are using some random pattern rather than checkerboard, maybe the accuracy may not be that accurate compared to the standard checkerboard-based method because of the matching and maybe scale factor thing. But it's pretty simple. So the main practical problem we have is we wanted to use this Panoptic Studio for social study, meaning we need to capture a lot of people's motion. And we needed to do this calibration in every kind of single day to do this capture. So we wanted to have really fast method and really easy method so that everything can be automatic. This method is good because it takes just 5 minutes for the capture, and everything is fully automatic. And it can be applicable for different types of sensors as well. Take-home message here is, so basically for calibration, there are 3 basic steps. You need to do some matching, and then you initialize the parameter, and finally you do bundle adjustment to optimize everything. Maybe the second and third part would be very standard in any calibration method, but according to your application, you need to consider the first thing, what type of pattern you need to use. I mean, what type of coverage you need to have, for example. At the end, I will just share a couple of more interesting stuff in our system. We do have audio recording, and that is also synchronized with the cameras. That's only because we have this special kind of production camera which already has that port for the audio. But although you don't have that kind of camera, still you can do that. A way is you just record clock and audio together using this kind of converter so that each audio has some timestamp together. Actually, in our system, we haven't considered lighting that much. This is our very initial lighting system, which has obviously motion blur. Because it's too dark, we need to increase the exposure time. Our current solution is also not that fancy. We are just using just usual tube kind of lighting. The only goal we had here is we wanted to get some brightness because Kinect has some auto adjustment for the iris. So we just wanted to have some brightness, and our cameras are not that high frame rate, so maybe this tube was enough to our purpose. So for the next talk, Tomas will talk about how to build this 10 Kinect small multiview system.
So I'm standing between you and the break, so I'll try to be quick. So as you'll see in a moment, having a multi-depth camera system, especially when they are Kinects, is actually quite complicated. So why bother, I guess, is the question. We already have these VGA systems. We have the HD cameras, and now we're going to add Kinects. Why do this, right? And the reason we do this is because the Kinects have a depth sensor. And having a depth sensor obviously gives us a very quick way to get a 3D reconstruction. So you have the color, you have the aligned depth, right? And then you can get a 3D reconstruction. This is what you would get from one sensor, right? The camera is on this side. And you can see that there are many holes. And this is because we only have one view, right? So as Takeo was saying, visibility is the main problem. So our idea is quite simple. Let's just add many more sensors. We have 10 sensors. And with 10 sensors, you can do something like this. Oh. There's some nice music to this. So the point here is that this is this is sort of direct output from the Kinects. This is not a reconstruction. So this is a very computationally cheap way of getting a reconstruction. And so the first thing we had to decide is where to put these Kinect sensors. So this is the dome, right? And we first started with 5 sensors. And the reason we started with 5 is because we thought they might interfere quite significantly, but it turns out they didn't. So the first 5 we placed there sort of at head level if you're sitting down in a concentric circle, and this is the sort of views that you get from that. And then the next set we placed a little bit higher so that we would get more coverage. So the reason we did that is to get better spatial sampling. So you'll see in a second. This is what you get from one Kinect. This is about 2 million points because you have 512 by 424 pixels. But actually, because we have a fairly large capture area, so it's a room of about 5 meters in radius, it's actually not that many pixels. So we added 5 Kinects. That's about 10 million points. And this is much more detailed. Obviously, you have all sides of the object, but there are still some holes that you get in certain places. So we just went for 10. It's twice as much, 20 million points. And now there are not that many holes. But actually, in practice, because our capture room is quite large, if you look at the number of points that actually fall on a single person, that's about 50,000. So in terms of accuracy, it's not a very accurate system. So as we'll see later, probably from the folks at Disney, when you're doing actual capture of humans, you might want even just 2 million points, even just on the face, not only on the whole body. So precision is actually an issue when you are combining multiple depth sensors. And the biggest issue is not in spatial resolution, but in temporal resolution. So the problem with the Kinect sensors is that we cannot synchronize them at the frame level. So as we saw, we have 3 subsystems. The VGA system, which runs at 25 frames per second. The HD system, which runs at NTSC, so that's around 30 frames per second. And then the Kinects, which run at 30 hertz. Now, the problem is that the Kinects are not entirely synchronized with each other. So they all start capturing at different times. So you get something like this. Each Kinect captures at a particular time instance. And between every frame, it's a 30 hertz signal, but they all start at different times. So what happens when you have fast motion is that you get this sort of artifact. So in the color, you can get motion blur, right? But when you're putting together the point clouds from many depth sensors, you get artifacts because you capture the image at different time points, especially when there's fast motion. So this is how that looks in a video. This is a dancer, obviously. And you can see the ghosting and how the limbs get elongated as a motion trail, because we're assuming that all of those frames are captured in a single instant. So the only reason we're even able to get this result is because we are able to put all of the Kinects on a common timeline. And we do that with a small hardware solution. It's this thing that you see here. And the purpose of this is quite simple. It just pipes the synchronization signal, which is the LTC timecode signal, into the audio ports of the Kinect. So when you go back to your capture software and you read the audio signal of the Kinect, you get a waveform like this, and this is the LTC timecode. And as was explained before, this portion here, you get a particular encoding for every frame. And it's just a signal that encodes a frame number. And this comes from production cameras, so actually the frame rate is NTSC rather than the 30 hertz of the Kinect. And the nice thing about this is actually that it's quite simple to use in software because it's a standard protocol, so you just use libltc or some other library to decode. So once you have figured out the starting sample from the synchronization signal, you can just relate this to the relative time of when a particular frame is recorded and put everything on this common time base. And that's how I got this graph here. So let's see how this looks in terms of hardware. We have the dome. We have the Kinects mounted on the inside. And there's obviously the synchronization signal, which comes from the HD camera system. And then the important part is that we have a capture node mounted on the outside of the dome. And this is how that looks in practice. You can see these 2 small boxes. These are small capture node computers. We use gigabyte bricks, but this is from like 3 years ago, so they probably don't even sell them anymore. But something equivalent would be on the market. The important reason why we have these mounted on the dome is that the Kinect connection to the capture node itself is a USB 3 connection, so you're limited in the length that you can use. There are ways around this, but none of the ones that we tried were very stable, so we just went with this solution. So in addition to this single capture node, we have 10 Kinects, right? So they are all networked with just basic Ethernet. And I'll make one small comment here, which is that if you're trying to do a real-time system and transfer both the color and the depth, the raw stream is about 145 megabytes per second, which is quite a bit. So it's slightly over a gigabit Ethernet connection. So you would need more than 1 cable if you wanted to do a real-time system. So more than 1 gigabyte, more than 1 gigabit Ethernet connection. So we've built this whole system, and the question we have is this enough? Is this enough to get nicely synchronized frames? And it turns out it's a little bit more complicated than this because each Kinect has two sensors, right? There's the depth sensor, there's the color sensor. And they don't acquire frames exactly at the same time. So the depth frame is a completely different sensor, and even though they are synchronized, meaning that the time between the captures is constant, they are completely different types of sensors. So the color sensor is a rolling shutter, which means that actually it doesn't capture a frame at a single time instant, but captures over an interval of 25 milliseconds. So frame capture starts here and keeps on going for 25 milliseconds until you capture the entire frame. So to give you an idea of how that looks, here I'm waving a checkerboard in front of the camera, and I'm moving the checkerboard to the right. So if you do corner detection and you try to assign a single location to the checkerboard for the entire frame, you'll see that you cannot do it. It's impossible to line the corners up. And this is because the top of the frame is captured about 12 milliseconds in the past with respect to the center of the frame, and another 12 milliseconds in the past with respect to the bottom of the frame. So if you look at the corners here, you'll see that the detected corner, so the corner in the image, is actually at a different location from the corner of the checkerboard at the time of the center of the frame, if that makes sense. So this is not just something that you can see with checkerboards. Every time that you have fast motion, you can see this. So this is, I'm overlaying the depth information on the color image for a single Kinect. And you can see that there's a mismatch between where the hand is when the depth was acquired by the depth sensor and when the color was acquired by the color rolling shutter camera. And if you have fast enough motion, you can definitely see that show up as those sort of misalignment between the depth and the color, not just because the cameras are displaced. So the take-home message here is that this is actually quite difficult to do. So on one hand, you get these cheap sensors that you can just buy and you can use very quickly, but you'll have to deal with all these synchronization issues and some interference issues. The second thing is if I were to do this again, I would try to avoid modifying the hardware of the Kinect because it's actually quite difficult. So I would try to synchronize the computers instead with PTP or maybe even NTP and see if that is enough synchronization to get the similar answer. But it's not all doom and gloom. The nice thing about this system is that it's a very quick way to get a 3D reconstruction. So if you have the types of applications that we're interested in, which is just social interaction, there usually isn't that much fast motion like dancing and so on. So for us, it's actually a very good solution to get a very quick 3D reconstruction of the scene. So I'll just finish with a couple of notes on Kinect calibration. The big problem here is that on the color sensor, we see our projected patterns. But if you look at the depth sensor, which is the same as the IR sensor, there's nothing there, right? Because the projectors are just basic visible light projectors, not IR. So you can't see it, which means it's back to the checkerboard for this calibration, which is quite tedious. And what we typically find is that because we don't have the nice sort of interactive feedback system that Christian Theobald was talking about, you will almost certainly miss a spot if you don't do it with any feedback, because you're trying to get all the area, but it's actually very difficult to do. So I think the take-home message here is just that if you're trying to combine all of these different sensors, you'll require a specialized calibration that has to bridge the gap between all of these sensors. And the solution that we're currently using is sort of a compromise. We use the static sort of checkerboard pattern calibration to calibrate each of the sensors' depth with respect to the color camera, intrinsics and extrinsics. And then we put all of the sensors together using the structure of motion approach that Hanbyul was talking about. And one aspect I didn't touch on is that when you have multiple of these sensors, because they were not meant to be sort of used together, you can have additional interferences in terms of noise. I wish I had something intelligent to say about this, but it's actually very difficult to quantify how those interferences happen. So what we did is just try to space them out as much as possible. So I'll conclude here. I just want to say we have a break now, and after the break, we'll have Tava Beeler and Derek Bradley from Disney Research, and they will talk about how to do very high quality reconstruction of the face itself. Yes, so the break ends at 11?
Yes, we have a 20-minute break, and then we will come back here at 11 sharp.
Take a look at this video here. Okay, this is an old silence video, Charlie Chaplin, and it doesn't have any kind of word. They don't. All of you can very easily understand the major content, story, even their hierarchy, their feeling, and everything. That's because they are speaking face and their body. So from their body gestures and their gaze direction, their encode their internal feeling and message, and we can actually observe this kind of signals, and we can actually decode that so that we can understand their major intention. So this kind of thing is also known as body language, and there exists another term to explain this, which is kinesics. So this kinesics is about the study of the way in which a certain body movement and gestures serve as the form of this nonverbal communication. So indeed, I believe we are using this type of method in our communication, in our daily life. But it turns out understanding this or even defining this is really, really hard. Imagine that you want to make a robot which want to use this type of languages, for example. How to design the robot, how to make the algorithm is really completely unknown. Sapir even said that this is an elaborate code, but understood by all. And essentially, this is kind of the major motivation of our Panoptic Studio compared to other existing methods. So we are mainly interested in this social interaction among interacting people. So usually, we try to put multiple people inside, and they just do some very natural motion by themselves. We capture their motion, and we really want to measure their motion. And this is kind of very common example captured in our studio. So multiple people are doing some social games. So we just instruct them some game rules, and they don't know about the game, the goal of this project at all, so that we can have some unbiased behavior. Suddenly, in this kind of negotiation game, they started themselves, which is really surprising for us. And this is kind of our output.
Let me talk first.
First, we can reconstruct their very sparse 3D landmarks. And also, we can have their bodies from this reconstruction method. And obviously, you may notice that some very important signal is missing, which is so in our method, we can also reconstruct their hands based on the recently developed our hand detector, which actually will be introduced in this CDPR. At the end, we reconstruct their body moving trajectory of much sparser than the Szabo's methods, for example, Szabo and Derek's, maybe to understand their social behavior. So let me just go through some example results we have. We can reconstruct their volume using very simple visual holograms. Very, very standard simple algorithm, but we have that essentially provide us this type of result. I just reconstruct each frame just separately. For example, I don't know how each point is moving over. What we really want is their movement, their motions, similar to macro-based motion capture system. So in this particular project, our goal is to get their very dense 3D trajectories. In this case, I did 100,000 point of movement in this case. The algorithm is just pretty simple. So we have, let's assume that we have a 3D kind of structure at time t, and our goal is to get their motion. Project the point on all the views, and we the optical flow information, and we just backpropagate that back the movement. So it's a pretty simple algorithm, and under this temporal correspondence problem within each view. However, although we increased, it turns out something is missing, and that is actually time variation. Now we want to use this optical flow information to know how each view is observing, when each view is observing which point. So what I mean time varying visibility is something like this. Let's say we are targeting this point here, and we are tracking the visibility of that particular point. The blue pyramid here is the visibility set where the target is visible. So we compute this type of visibility for each point, and just based on the optical flow from this visibility set, we can track the point for a long time. Share you some of our examples. This is, I think, 2014, and Hyun and I, as a student in CMU, we did this volleyball game. Trajectories of us. Since our method doesn't assume any kind of human, they are. Yeah, this is pretty interesting, and this is, and we can have this visibility for each point. And this is a bit crazy example. So here, I was actually a fan just to see whether this is working. It's of course it's a bit noisy because basically at the moment we didn't have good lighting. But still you can see, interesting the movement of the flying confettis. So in this, up to now, we volume reconstruction and maybe trajectory reconstruction. We don't know still which part is hand. So you have their body motions. So this is them. So we can have multiple people. And the major source of doing this is this 2D detector. So the kind of our major preference is we wanted to do body capture for many, many people, like 100 or 200, for example. And we really don't want to do their body scanning because basically they don't want to do, they want to spend basically it's somehow annoying to have their body scan for every individual. So we don't want to use just minimum assumption. We want to have just minimal assumption about the scene. And this is a way to do that. We just run detector, and we just, our method is just based on this detector. This is our recent version, and that will be so we just run this detector on each view, 2D skeletons. And the way to do that, to together in 3D. And the way is pretty simple. And for each part, we generate a 3D heat map. For example, in this case, let's assume that we have 3D space. And each voxel point, we just project that to all the viewpoint, and we just average out them. And after some thresholding, we can get this kind of candidate point for each joint. It means each joint. So we have some candidate, and we merge them together in the bottom-up sense. And now some skeletons from a dynamic programming. And at the end, based on the temporal method trajectories, we just merge them together so that smooth out skeletons. And also, we can label part is the trajectories of the leg or trajectory of the body. the key advantage of our method is we don't assume their shape, everything is just unknown. We just reconstruct them from the detection only, which is really easy to do this kind of social study. And let me just give you some interesting examples here. This is a game named a mafia game. And there is some hidden mafia and hidden citizens. And based on this discussion, they need to figure out this.
No, I'm just making, doesn't mean that you are the ones who have been killed.
And this is 3D construction.
I mean,
And this is projected on the on one novelty.
No, I'm saying, I'm just trying to see who.
Another very interesting thing is this. Since the size of the person, for example, it can also capture. Actually, she's my wife and he's my son. I'm so that I can see his kind of development. This is another game. Since we have many camera views, it's actually working well, although we have this kind of occlusions. It doesn't have to be social motion. It can be any arbitrary motion like dancing. Or maybe some musical performance, which will be also very interesting. And let me just give you some kind of interesting finding we found. So since we have 500 sensors, we can do some kind of study, like how many cameras do we need to do this kind of reconstruction. So this is PCK curve, which is kind of popular in motion estimation method. So x-axis is threshold to determine the number of inliers. So the threshold means the distance from the inlier ground truth data. Here, ground truth data is actually just using the full number of cameras in our case. Y-axis is accuracy, the number of inliers. So the higher, the better. So we vary the number of cameras, and you can see if we have more cameras, obviously the result is better, but there exists some saturation. For example, 160 and 300 cameras, they provide almost similar result. This is the case of 2 people, which is pretty simple. But let's say we have 7 people, then obviously accuracy becomes down. And you can see maybe the more camera is more important in this case. So it's completely application-wise, application dependent. If your application is very, very complicated, then you may need more cameras. If your scene is pretty simple, then you may have just 10 or 20 cameras. Another interesting thing is this. In our particular application, it turns out the resolution is not that important compared to viewpoint. So using the same 19 cameras, I just vary the resolutions. And it turns out the accuracy is pretty much similar. But when you consider the budget, pixels of this particular case, that is similar to 128 VGA cameras. But when you see the accuracy of those cameras, which is much higher, meaning in this particular case, our resolution is not important compared to the viewpoint. That's only because we are using this pose detector, and that anyway resizes the image before we use the neural network. And okay. And for the next talk, Tomas will talk about more interesting part.
So we've seen the bodies, I guess. And so I think let me just play these 3 videos, and you can have a look to see if you can understand what the people are doing in the scene. Right? And it's pretty obvious that if we don't have say, the faces, a lot of the information is lost, right? If we add the faces, maybe you can get a little bit more of an idea of what the people are trying to express. And finally, when you add the hands, I think it's much, much clearer to us, at least, how the people are interacting, I guess. And so face detection, there are many facial key point detectors available. Here I'm showing just one from Fernando de la Torre. There are body key point detectors available as well. This is just from this CVPR, but even in previous CVPRs, we had some detectors available. So why not do the same thing for the hands? And indeed, the method that we're going to use is exactly the same as we use for, say, face detection or body detection. We just have an input image, and for each key point that we want to detect, we produce a confidence map of where we think that key point is, right? So it's 0 everywhere except where we think the key point is, and there it's a 1, a peak, ideally. So this is exactly the same as faces and bodies, right? So why hasn't this been done, right? So as we all know, we just apply deep learning, and it's just going to solve everything for us, right? The problem here is that we don't have the training data, right? That's the key component here missing. And in fact, when you think about how much time we spend, working on all of these areas, it might look more a little bit like this, because curating a data set of accurately labeled images is actually very, very time consuming. So what we did is, you go out, you paste flyers, you try to get annotators to do this for you. It's difficult. And for some things, it's actually very difficult. So say for hands in particular. So I was wondering, why hasn't this been done for hands, for example? And I think the reason is because hands are quite difficult to label because most of the joints are occluded. So if you look at a fist like this, from any particular viewpoint, a lot of the joints of the hands are occluded. So that's an image that one of the annotators annotated, and I was not happy with this, and I said, I think it should look more like this. But in reality, it's just a guess, right? It's my guess versus someone else's guess. And this happens actually for a lot of joints. So internal joints, like the knuckles, are also hard to localize for people because, it's sort of, so if you look at the hand from the side and you see where the joint is, people tend to think they're higher than they actually are. And this happened across many annotators that we had. Anyway, so annotating manually is complicated. Maybe it doesn't scale very well to many other applications. Let's say we want to do not just the hands, but other parts of the bodies, right? So the obvious other alternative is synthetic data. So here, that's what I tried next. Unreal Engine, let's see what we get. As you can see, it's not really real images, right? You move on to a better renderer, say ray tracing. This is what I did here. And still, there's a mismatch between reality and what you get from these images. And it's sort of a chicken and egg problem, right? Because how do you generate realistic hand poses if you cannot capture realistic hand poses, right? So that's sort of the approach that I'm going to talk about here, is sort of trying to get around all of these problems. So let's say we take a detector trained on this synthetic data and we run it on an image. It's not going to be a very good detector because they don't really match, right? But if you have a multi-camera system, you can have other viewpoints of the hand, and maybe some of those viewpoints are easy enough for the detector to work, right? So if you have enough camera views, you can probably get at least 2 good views of the hand, 2 easy views where you can detect a particular viewpoint, right? And in our case, we have 30 views, and I'm only showing a few of them here, but you can see that for any given viewpoint, for any given key point on the hand, you can probably localize it on several images. And once you have 2 images, you can do triangulation, say, for example, doing ransom. So the idea here is we run our initial detector on all the views that we have. For those views where we actually get a good detection, we do triangulation. And then we can reproject that triangulated image onto all of the other views, right? So we have suddenly converted a detector that was pretty bad on this particular view into a good detection. So we've annotated the image. And we do this for every viewpoint that we have, right? So in every iteration, we generate a lot of training data. So taking this newly labeled annotated images, we can retrain our detector. And if we retrain the detector, we see that now suddenly it works on this view because we had a training image that was very similar. So just to give an idea of why when this works and when it won't, right? It's not magical. So it works because inconsistent detection, so bad detections, will not triangulate to a unique 3D point, right? That's the way that we're discarding bad detections here. But when you have enough camera views, so even 30 is enough, sometimes get false positives. And this is that you sometimes get false positives, right? quantify exactly how many camera views you might need for a given quality. Show some results. So render data, so synthetic data, you'll see that actually it almost never works. We do have 30 views. I'm not showing all of them, right? So the point is that these initial detections are pretty bad, right? There's all sorts of mistakes almost. Even so, when we do a robust triangulation like with Ransec, you actually for this particular frame. And when you reproject them, it looks like you have labeled your images. Ransec and reprojection. So run the detector again after retraining. The detector now, the errors have been fixed. So that's the initial one. So here's a visual comparison of that. So that's the initial detector. And here is after retraining. Now, and we also have many image frames. So we don't have to use a particular image frame. We only use it when actually the Ransec triangulation is confident in the training example. And we can iterate this. Use any garbage into our annotations, it will just keep getting better or stable. So here you still see some mistakes. This result removed. So I'll just show some examples. Here's an example video that now we can do. So what I'm showing here are after reprojection. It's not an individual. Do sort of a hand detection for multiple interactions. So most hand detection methods until now have been depth. Depth-based methods have difficulties with object interactions and resolution-wise, it's to reconstruct the hand, which makes it difficult. So we were quite surprised that object interactions also seem to work quite well when you're using images versus depth. Depth, you usually get confused with like ICP, trying to establish correspondency, whereas this works quite robustly for theme of showing Hanbyul sun. The nice thing about this is that we don't need a model for the hand. So if the hand is much, much smaller, we can still detect the joints. Typically doesn't happen when you're using a model-based tracking method because information of the hand. So that size difference. The idea here is that we can apply this to pretty much anything, right? So this is our basic key point detection. I trained a key point detector on, say, a bunch of standard data sets. I'm listing some of them here. I probably used some other ones. But, and you know, it works quite well if you have a frontal face. But if you run it on a different viewpoint, say a side viewpoint of the face, they tend not to work at all. And this is because there are no manual labels of these kinds of images in your training set. And part of the reason, at least, I mean, you can say, okay, let's just pay people to annotate. But the problem is, so for profile views, this is hard to do because you don't know where half of the points on the face are, for example. So if we apply the same method that I was talking about, just, you know, we triangulate, we reproject, we retrain the thing. This is the detections that we get after one iteration. Now suddenly it works on different viewpoints, right? And so this is here what I'm doing is I'm retraining on this same sequence, right? So these images were actually in the training set, so to speak. But these are held out images. This is the initial detector trained on, you know, manually labeled data. And then after one iteration, we can get you know, detection on viewpoints that are quite difficult for manually labeled data. And so the goal here, I think, is trying to use these multi-view systems as a way to generate training data for deep learning so that we can actually use all of these things outside of the dome, right? And that's sort of the effort that we're kind of pushing with. This is an open source thing that you can download. We call it OpenPose. And what we're trying to do, similar to what Christian was saying, is we're trying to start moving away from, try to use the Multiview system to generate training data so that we can move to much simpler sensors, say one single viewpoint. We'll show a demo of this Tuesday, one of these days, anyway. So I just want to finish up just by saying that all of the data is going to be online. We've put up most of it already. We're essentially just uploading more of it. We call it the Panoptic data set. The URL, I'll paste it afterwards. But you can see that you can just browse a bunch of sequences. And the types of data that we try to capture is these social interactions between naturally interacting people. And what we're trying to do is richly annotate these with all sorts of labels, in particular with phase landmarks, hands, bodies, and tracking through time. So sort of as an overview of what we're capturing in the dome, we have all of these multi-view input images. We apply all of these detectors that we're trying to get as detailed as possible, subject to limits of resolution in our camera systems, which we then triangulate so that we have labeled data in 3D. And in addition, we have the Kinect subsystem, so synchronized up to what precision we can get. We have multi-view RGB-D images so we can get an aligned point cloud of the same scene reconstruction. And we're going to try to upload all of this data. So parts of this are already available, and we're working on uploading the rest. And with that, I'll just finish, and if there are any questions or... Yeah. So the nice thing about the method I explained is that because you're using triangulation, it always corresponds to a 3D location. The only problem is that 3D location might not be the center of the joint. So it could be some other 3D location, and you can have drift. We don't have a good solution currently. I think, so what we've been doing in practice is we just sort them according to criteria in terms of the confidence of the detection and the reprojection error. So we sort them and hope that the top ones that we use for training are the best. And then we have a final pass where we just look at them and see, okay, looks fine, train. I don't have a good answer, sorry.
For the head-post tracking, so the back and the front and back is very different. So
correct.
Are you associating the same joint for the back and the front?
Yes, so when we thought about the key points to use, we actually wanted to use joints. So we tried to, so it should be the location of the 3D joint inside the hand, which is a unique location, more or less. It obviously looks very different from front and back.
But the position is different.
Well, the joint is one point, right? It's where your finger rotates around this. I mean, obviously it's an approximation, but maybe we can talk afterwards.
Okay, so thank you for staying with us. This is the last session. So I'm going to give you the last session about our system, and also we're going to do the live demo of the markerless motion capture system. So we have been talking about the multi-camera, building a multi-camera system, in terms of a key design factor: precision, diversity, and scalability. Okay? So we use this term to describe our system in terms of hardware and computational model. The question is, now, can you build your own Panoptic Studio? So learning from this, can you build your customized solution? Okay? And from my experiences, this involves not only this high-level task, but also low-level engineering issue in practice. Okay? So in this talk, I would like to address these questions, like low-level engineering issues of building a multi-camera system. Okay? So, and I realized that many engineering issues stems from the budget and space-time constraints. So this is come from my personal anecdote, where last year I was appointed as an assistant professor in Minnesota, and I got some decent amount of startup package to build my own research program. Okay? And I really wanted to build a multi-camera system because my research is related on measuring the human sensory motor skill. And since the startup package is limited and also very precious, personally, so I have to think really, really deeply how to build a system, how to spend my money to build a system. Okay? So in terms of, there's like some cost, but the constraint. How much should I pay? How much should I spend? And if I are given to $60,000, equivalent to the Bicon system, how many cameras can I fit into this budget? Okay? Not only for cost, but also the budget allocation is important. Depending on the choice of your camera, your whole camera, the system configuration can be changed. Okay? And there's also space and time constraint. Okay? When I start, I ask for the space to fit my multi-camera system, and they assign me a small room in the computer science building, okay? And with some condition. The condition was I have to move my system at least 3 times within 2 years, which I thought it was quite ridiculous because I don't want to break my system by moving. So, but I have to meet this condition. So I have to think about, I have to redesign my multi-camera system that is reproducible. Okay? I should be able to replicate this system very easily with the limited human resources. 1 or 2 grad students should be able to build the system within a reasonable time frame, such as 1 or 2 weeks. Okay? And also, the system can be broken. Some part of the system can be broken. And it should be easily replaceable. Okay? Third, I'm an assistant professor, so I'm supposed to keep producing a result. I can't wait for 5 and 10 years to get the result. So I have a time constraint, and if I have an idea, it should be easily implementable, and the building upon open source is more favorable. Okay? So I have an additional constraint to build a system. And I think many of you also have this constraint too. Okay? So when I built the system, I realized that the camera system used for the Panoptic Studio was obsolete. So I cannot buy the system, and so it's not my option. So I looked for the other solution, and I found that some cameras, multi-camera system designed by Point Grey that connect to 12 cameras. Okay? The way it works is there's a camera. It's directly connected to the CPU using it as USB 3 connection, and data is written in the drive. And there are 12 copies of these cameras. Okay? And the way synchronizers work is there's a master camera that trigger the rest of the 11 cameras using a GPIO cable. Okay? So this is how the system works. The question is whether this is scalable. This is suitable to me. This may be suitable for the small-scale cameras. Maybe it works for 12 cameras with low frame rate. But if I want to scale this up to 70, 100, or 200, is it even possible? So there's one big problem, which is synchronization. Synchronization signal generated by the master camera attenuated if you're adding more cameras. Okay, so there's a sync attenuation problem. And another problem is the PC has a limited USB 3 support. Okay? And there's a huge communication and computation bottleneck happening here. Okay? There's like a big problem. So we have to solve this problem, and and let's do a little bit of math here. Okay? So how much data will generate from the 12 cameras? Okay? So each image is about 1.3 megabyte per image. Okay? And if you have a 200 frames per second, that is translated to 60 megabyte per second. Okay? And if you have 12 cameras, then it is about 3 gigabyte per second. Okay? And this is a huge number, and it can actually even fit to the one SSD. Okay? So we need to have a little bit better solution for this. Okay? So, and even high-end motherboard that can host like a 7 PCI can only go up to 28 cameras without any SSD saving. So we can write anything onto our disk if we have this configuration. So we need a better solution for this. So here's our system where we have 70 cameras surrounding this space, where each camera is connected to the USB connection and GPIO connection for the synchronization. Okay. So this is all the small cameras, calibrated cameras. Okay. And using this camera, we can get the high frame rate and high resolution from these settings. And this is 3D camera extrinsic calibration of the system. Okay. We just got the result like 2 days ago, actually. All right, so how do we solve this problem? So first, sync signal attenuation problem. So this is also related to my budget issue. Okay? I would like to have a huge emphasis on optics and computing because I want to focus. I don't want to compromise with the precision. So I want to have a huge emphasis on optics and computing. Then I can only spend less than $2,000 for synchronization. And if you buy the GPIO cable, which is about like $25, if you multiply with the 70 cameras, then it is already, I already saturated for my budget for the synchronization. So I need to have a better solution. I can't have any luxury for such as function generator or signal distributor for synchronization part. So how do we solve it? So what happened here is that there's a master camera that sends us trigger signals. Okay? If we measure this signal from using an oscilloscope, this is an electric pulse generated by the master camera. Okay? And the shutter is open at the falling edge of here. And note that the magnitude of signal is about 3.3 volt. Okay? So if you add more cameras, what happened here is that the magnitude of signal reduced. Okay? So why this is happening? Okay? So let's go back to high school physics. We have a master camera that generates the electrical pulse, which is about the 3.3 volt. Okay? And this signal can be, the current can be generated by adding a resistor on this. And note that the current is equivalent to the capacity of the master camera. So we can go beyond this current. Okay? So if we add a slave camera over here, which is translated to the electrical resistance, then due to the serial connection, the voltage over here is dropped down a little bit due to the Ohm's law. Okay? Let's add more cameras. Okay? If I add one more camera, then the net resistance here is go down to half because of parallel connection. Then the voltage we can measure here is like drop down to 2.7 volt. So, so that means that if we keep adding more camera, then the voltage over here will drop down to almost 0. Okay? So after adding 50 cameras, this is the signal, electrical pulse that I can observe from the oscilloscope. Okay? So we can trigger my signal, my slave camera with this signals. Right, so our solution is we adding a transistor that can drive the current, okay, with the external power supply with a variable resistance. The role of this variable resistance is controlling the amount of current that will pass through this camera. So no matter how many cameras you add here, you can, by changing this resistance, we can keep the voltage over here as like 3.0. Okay? And this setup can be easily realizable using a very cheap the AC/DC power supply, which is less than $5. And this actually is a simplified version of the operational amplifier. Okay? So this is we have a operational amplifier diagram here, okay, that can drive the rest of the all cameras. All right, so using this operational amplifier, we can recover our signals up to like a 3.3. Okay. All right, so this is the actual the physical realization of our system, where there's the master camera goes in this direction, and there's a operational amplifier made of the transistor and trigger the rest of the all cameras. And in addition to the electrical part, we have a hardware that we print using a 3D printer. Right, so we solved the synchronization problem. What about the second problem? Limited USB 3 support. So note that the size of the data we are talking about is about like 3 gigabytes per second, only for the 12 cameras. And there's a huge bottleneck, communication and computational bottleneck on this CPU. Okay. This CPU can even process like even simple image encoding for that high frame rate. So we need to have a better solution. The way we solve this is instead of putting big computer here, we distribute the computer to each camera. And the primary role of this computer is the JPEG compression. It just compress data from 260 megabytes per second to 20 megabytes per second. Okay? And this is a physical realization of this PC, where we use a single board computer that is capable of having two cameras, two USBs, and it can process. It is strong enough to process the image processing on that and compress the data. Okay? And so before moving forward, we have to validate whether this compression makes sense. Okay? So this is a raw image, which is about 1.3 megabyte. And this is a JPEG image, which is about 150 kilobyte, almost no change. And this is a pixel difference, intensity difference between the raw image and JPEG compressed image, which can have up to 9 pixel difference. Okay? So let's compare on the SIFT. If we run the SIFT on the raw image and JPEG image, that produces almost equivalent performance. And also, if we run the structure from motion on these images, they also produce the equivalent things, which produce about the 6,000 point cloud. Okay? Right, so we have this solution where we can compress the data through this single board computer. Yep.
Would the compression setting use like 99% or?
Yes. And this computer, the computational module is quite modular, because if we want to add more computation, like convolutional layers on this, then we can just replace this Odroid with this kind of NVIDIA TX2, where it can run multiple layers of the convolution. So this is the system that we have, where there's a small Odroid connected to cameras, and that the camera is communicate with the main server using the network switch, okay, 10 gigabit network switch. And this network switch is strong enough to drive up to 60 cameras at 200 frames per second. Okay? And so this is a realization of the network switch, 10 gigabit network switch with a 48 port. So comparing to the previous centralized system, which produced about 15 gigabyte, our system produced about 1.2 gigabyte per second. Okay? By this, adding this small computational unit just in front of the cameras. And still, this number is big, so that we need more SSD. So finally we have this kind of configuration where there's a multiple CPU, the multiple thread is saving to the SSD separately, independently. So here I would like to summarize our budget. So I wanted to have a strong emphasis on optics. So which I spent about $35K for the 70 cameras, including lens. Okay. And for the computer, the CPU, including Odroid and server, it cost about $10K. And for the GPU, we spend about $8K. But if you want to run a more convolution layer on this camera, then this price can go up. And the storage, we spend about like $3K, including multiple SSD and hard drive. And for hardware, we spend about 1.5K. And also network switch is a similar order. Okay? So the grand total was about 60K. Okay? So we can build the 70 camera system with $60K dollars. And note that all components here are the off-the-shelf component where we can buy from the online vendor. Okay? So before conclude, I would like to show you our demo here, real-time markerless motion capture system. Okay? And the system configuration is that there are 11 cameras. There's 11 cameras here. And that connected to the small Odroid on the table. And there's a network switch. And then that communicate with the main server in this big box. Okay? And we add 3 GPU that is responsible for the open pose. Okay? It gets the image and it runs the open pose for each frame. And then we do the triangulation to do the markerless motion capture in 3D. Okay? And in terms of calibration of this camera, so we use a standard structure from motion. The code is available in our GitHub. And it runs image distortion, undistortion, and shift detection, matching, and bundle adjustment using a set of solver. Okay? And this is one of the example of the 3D extrinsic calibration for this system. And for the client side, we have open source. We use open source ARM drive, the camera driver that can grab the image from the camera. And then we have 2 implementation that transfer the data to the server using FTP and TCP/IP. And all the code is available in this GitHub as well. And in the server side, we have a multi-threading Odroid access. And in using this GPU, we run the open pose for each image and run the triangulation to get the 3D point of each joint. Okay? So this work is mainly done by our team, especially the Yubin Wang. And this is conclude our tutorial. So this is Again, I would like to acknowledge our contributor of the Panoptic Studio over the world. And this concludes our tutorial. Thank you. So if you guys are interested, you can come here and do some Road 9 demo.